Hello, my name is Endrit Hoxha and I am a lecturer at Epoca University. Today I will make a presentation within the framework of Key Force program. The subject of presentation is the influence of design parameters in fire safety of structural beam elements. The plan of presentation: importance of structural fire safety analysis, design approaches, critical temperature method, case study, influence of design parameters, and conclusion. But why a fire safety is important? In 1967, due to a fire, 322 people died in an innovation building in Brussels. In 2005, a fire occurred in Windsor Tower in Madrid, Spain. The building was under fire for around 20 hours. The structure of the building had a lot of damages. Both of example presented has not been designed for fire safety and consequently has not been protected. An example of protected building was that of the Interstate Bank in Los Angeles. As can be seen in the slide, only 3 stories are destroyed from the building. Some example of the consequence of fire and how they destroy the element of the steel structure. And for reinforced concrete structure, at the end, the key objective of fire protection is to limit to acceptable level the probability of death injury, property loss, and environmental damage in an unwanted fire. Fire resistance of steel building structure can be assessed in terms of time duration obtained, in terms of fire resistance capacity, in terms of critical temperature. Fire resistance design of steel structure. Member analysis. Fire resistance design of steel structure, analysis of part of the structure. Fire resistance design of steel structure, global structure analysis. For 3 types of analysis, there are 3 types of methods: simple calculation, critical temperature, and advanced calculation method. In this study, we are focused in critical temperature method. Step 1. Determination of applied design load to a steel member in the fire situation. A recall of force applied in the structure of a building are presented in this slide. They can be classified in different ways. Design situation shall be classified as follows: persistent design situation, transient design situation, accidental design situation, and seismic design situation. The combination of action for fire situation can be expressed by the equation. Combination coefficients are given in the tables of Eurocode 1. Step 2. Classification of the steel member under the fire situation. Class 1. Cross-section are those which can form a plastic hinge with the rotation capacity required from plastic analysis without reduction of the resistance. Class 2 cross-section are those which can develop their plastic moment resistance but have limited rotation capacity because of local buckling. Class 3 cross-section are those in which the stress in the extreme compression fiber of the steel member, assuming an elastic distribution of stresses, can reach the yield strength, but local buckling is liable to prevent development of the plastic moment resistance. And class 4 cross-section are those in which local buckling will occur before the attainment of yield stress in one or more part of the cross-section. Step 3. Calculation of design load bearing capacity of steel member at instant t equal to 0 of the fire. Step 4. Determination of degree of utilization of steel members. Step 5. Calculation of critical temperature of steel members. In summary, the critical temperature is function of span, self-weight, and combination coefficient. Step 6. Calculation of the section fire factor of unprotected steel member and correction factor for shadow effect. Correction factor for all cases and correction factor for double T shape. Step 7. Calculation of the heating of unprotected steel member. Increase of the temperature. In summary, temperature of the beam is function of only section factor. In conclusion of this third part of presentation, we can say that the structural fire safety is function of span, self-weight, combination coefficient, and section factor. In the following, the method is applied to the case of a steel beam with span of 3 meters. Load applied to the structural members are calculated with the equation. Then are evaluated the internal loads and the minimal required plastic moment, the degree of utilization, and the temperature, critical temperature, has the values. After the evaluation of the increment of the temperature in the steel beam, we find that the time to reach the critical temperature is 11.2 minutes. In order to evaluate the influence of design parameter in fire safety of steel beam, 35 cases are created by varying span between 3 to 9 meters, combination coefficient between 0.3 and 0.5, self-weight of slab between 250 and 700 kilogram per meter square, and section factor between 50 to 200 meter minus 1. Influence of variation of span in time to reach critical temperature and degree of utilization is presented in this slide. The influence of variation of combination coefficient in time to reach critical temperature and degree of utilization is presented in this slide. Influence of variation of self-weight in time to reach critical temperature and degree of utilization is presented. Influence of section factor in time to reach critical temperature is presented as well. In the end, the influence of parameters in time resistance of steel beam is calculated with the formula presented in this slide, and the contribution of design parameters are evaluated. In conclusion of this presentation, we have identified the parameters influencing structural fire safety, that is span, weight of slab, combination coefficient, and section factor. Optimal span should be considered 5 meters. Light slab structure are most adequate. Better to insulate than to increase the dimension of structural element. For all references for this presentation, please refer to the corresponding lecture paper. Thank you for your attention.